implement the DTC in the SRM. And you see that we try to measure the rotor position, and we require 4 current sensor, and the Park transformations is used to convert it to DQ, and the stator flux vector, and there are total 8 sectors in the conventional one, and depending upon the stator which it is in which sector, accordingly we are going to we have already a lookup table made, and during if the stator flux vector is in sector 1 or sector 2, accordingly the pulses are generated for the asymmetric edge bridge converter, and accordingly it will be given to the SRM. But the feedback, it will be current sensor and the position. So we have a reference torque and the reference flux, and accordingly according to the error generation and your sector. So because we need to know whether the torque has to be increased or decreased, similarly the flux has to decrease, right? So that is why we require the reference torque and the reference flux. Okay. So this is our initial selection DTC. So this is what I'm trying to say. If I want to increase the torque, increase the flux, then accordingly the full color is the vector. So suppose if the reference vector stator flux vector is in the sector N1, then the vector which is in the next sector immediately in the anticlockwise direction, that is selected, and then you can see that there will be you can witness an increase in the torque and the flux linkage. And similarly V4, and once these two are selected, then the opposite of the vectors will do the needful for reducing, and then accordingly the same is the case for the other sectors, right? So this is one, or I will use the podium. So here the button switch is there. I will use the podium. So the conventional the sector voltage vector selection or for the conventional DTC is actually called, we call it as improper voltage selection, and it does not result in the objective or addressing the objective what we try to address. So the main thing is you can see the second one, which is the SRM current drawn by different phases, 4 phases, so 4 different color, and these are the parameters which is taken for the simulation purpose, and the data we have got from so initially we don't have that SRM, so later on we purchased and then we could able to conduct the experiment. But before that we are grateful to Dr. Rajesh who gave that result from IT Delhi. So through that only we could able to realize the mathematical modeling and then later on simulation. So you can see the torque ripple. You see the torque ripple, and the second one is the current, and the third one is the torque produced by the individual phases. So 4 phases, 4 different types of torque, and the collective, the average of this torque will result in the motor, but still it will be having a ripple. and for different sectors how the voltage vectors are selected. Actually that is a fictitious one basically. So you don't need anything, because in the motor we can say that this, the moment when I give some supply to the stator, flux will be generated, and when there is a change in the flux and there is a stationary core, again the EMF is induced. So all those things will come into picture. Okay, but this is actually what we are saying is that stator flux vector is rotating in that fictitious, the 360 degree, and based on that we are just trying to switch on and switch off the individual phases, right? So you can see that there is the third one, the torque is below 0, also torque is produced. That means the negative torque is there, which is what we try to address. We don't want negative torque. And in the second waveform, if you see that, even though the current, for example, you take the orange one, orange torque, right? The torque is 0, but you can see that correspondingly on the current waveform, there is some small amount of current is drawn from the supply, which is also we are trying to address. Because when there is no torque produced, why the motor is still drawing the current? Okay, because this looks, even though small, when I show you the last part, then you will understand that the importance of that, right? Because when we try to, when we say efficiency, then we have to reduce the losses. So losses means again conduction losses, switching losses. So these contribute in improving the efficiency. The coming slides will show you that. And this is for one phase. So because you may get confused when I show for 4 phases. So that is why we have tried to show for one phase, and the gating signal for that particular one H bridge, which involves 2 switches, and the voltage taken during that time. So this is what I mean during the 0, supposed to be 0, but it draws some current. So a more clear picture, we have taken the current as well as the torque for one phase, and you see that there is a negative torque, and during 0 torque there is a current drawn from the supply, that we call it as dead zone. So what we try to initially address is that we increase the number of sectors, keeping the vector same. In that way, from 8 to 16 it increased. So we have better switching. So we don't need to wait for that 45 degree, and then now with the 22.5 degree, the stator flux vector will move, and then we will have a better option of switching on and switching off the devices. And this paid the result for us, and you can see that during the 0 torque, the current drawn from the supply got almost reduced to 0, but still the negative torque is still persisting. Okay, so by increasing the number of sectors, we try to achieve something, at least if not completely. Okay, and you can see that clear picture in a single phase waveform. And as I said, there is a negative torque still present, but during the 0 torque, the current drawn is close to 0. And also the reference torque, and then the conventional for conventional, and what we propose is the 16 sector 8 vector DTC. Then we were thinking that slightly, okay, we will we already increased the sector, why not to increase the vector also? But also there is one point to be remembered, there is a degree of freedom. You cannot keep on increasing and then say that I achieved a certain thing. That is also, that may be possible for publishing the paper, but practically also we have to check whether it is an optimal value. Means it should not be too low, it should not be too high. You cannot keep on increasing. So, but we increased that 16 vector from 8 vector, and then but before that we have also tried to implement this in Opal RT. So so one of the passed out of my student MTech, he was doing at that time a PhD abroad. So we took his help in getting this at that, because we don't have that Opal RT. So he was helping us at that time. So whatever we did in simulation, we also tried to verify it in the Opal RT. You know that it is software in loop, it is not hardware in loop. So that is something different. And then we could verify our results, simulation results in the Opal RT. For the same thing, you can that dead zone in the proposed, the P stands for proposed and C stands for conventional in the second one. Then these results are taken at 500 RPM. So as I said, the later on we also found that one of the major disadvantages with our, even though we could reduce the negative torque as well as the current during the zero torque, we could not able to increase the speed beyond certain value. Even though our motor is rated for 3000 rpm, beyond 750 rpm, our results are showing in a different way. So we have to stop at that point, but it is anyhow, it is a starting point to address the torque ripple, which is the major problem, which is the hurdle in using the SRM in the electric vehicle, right? So some of the numerical values, you can see that how the torque ripple is reduced and how the torque per ampere ratio increase. Because of that dead zone in that torque, the ampere drawn is 0, so we could able to increase that torque per ampere ratio and the publication out of this work. And then we propose for that 16 vector also, why not sector, we also have can increase and then check, and then this yielded the result. And again the even the previous presentation also he was telling about the optimization, right? So the optimum voltage vector is selected such that the magnetization of the outgoing phase is replaced by the freewheeling mode of the active incoming phase. Because what we observed in the 8 vector and 16 sector is that when there is a changeover happening in a particular, you take for example one phase, from the magnetization it has to go all the way to demagnetization. So it is skipping the in between one mode, that is called freewheeling mode. Okay, so that also we found that it become a burden on the system, and that is what it mentioned. So when I show the flow chart, you will get a clear picture of that. It's replaced by the freewheeling mode of the incoming phase, and the proposed method completely eliminates the magnetization of all phases under negative inductance slope region, which I was explaining in the first slide. So the negative inductance slope region, you should not do try not to do anything during that. So otherwise it will result in the negative torque also, or the torque ripple will be more, so that the phases does not produce the negative torque that improves T by A and reduce the torque ripple. So the number of commutations are reduced in the proposed method. That is also will be shown as a numerical data in the next, because I used to tell to my students also, whenever they come and tell that, sir, I improved the thing, I improved the system. Okay, they will never tell in terms of speak in terms of numerical value, which is very much important for engineer. Am I right? So I have to tell, in even though it is a 0.5%, I improved the efficiency by 0.5% or 1%. I have the efficiency is better now. Good, better, best and all will not work in engineering. Okay, we have to tell specifically what we achieve. Even if it is 0.25% also, we have to tell the fact. Okay, and other terminologies which we engineers or I found with the student is that they will never use the word conventional or such type of thing advanced. They will use normal diode. I ask them what is that, then what is abnormal diode? Right? So we have to say that, see, when I say power diode, I can say it's a small signal diode or low power diode. But still my PG student is still using that word normal. Okay, normal diode, or I don't know how to change. I think hopefully before he graduate, I will try to change his way of telling the technical terms. Okay, so this is how that 16 vector, 16 sector is realized, and the lookup table for that. And this is what I mean. See, this is the conventional, my right hand side, on the left hand side. You can see that it is -1 to 1. So that means the demagnetizing to magnetizing or magnetizing to vice versa. So which is what not desirable, outgoing phase demagnetizing to magnetizing. But in the case of 16 vector, 16 sector, you can see that -1 to -1 means either it remains in the next switching also, that it remains in the same, or at the worst case it goes from demagnetizing to freewheeling mode, or same magnetizing to freewheeling, and then means it goes, it will not skip any particular mode, it will go in the sequence. So that is what also we observed. So anyhow, these are all available, this data is available in the paper. And the simulation results, you can see that what I was talking about, the torque, the negative torque is now not present here. Okay, steady state simulation results of the phase voltage, phase current, and total electromagnetic at 250 rpm. As I said, that is one of the drawback which we presently we are trying to address this issue, 250 RPM, and then conventional and proposed, and then you can see the torque ripple also. It's if you say take the average torque, then this is better compared to this one. And then so this is the phase voltages VA and VC, phase currents, phase then torque per phase for the 750 RPM. So we try to show for 250 RPM, 750 RPM. That was the maximum. That's what I said. We could not able to achieve after that. And then same, the torque, the current waveform. So because so far we are showing it for per phase, and this is for the whole phase and the average torque, reference torque, and the electromagnetic torque produced. So how much it matches close to that, right? When there is a change in the speed, and this is the same is executed in the Opal RT, and we have verified that there is no negative torque and there is zero current during the dead zone, right, for the conventional and the proposed. And now we are moving on to the loss calculation and the torque ripple analysis. And the current stress is also an important factor. See, actually when we use MOSFET, you might have seen in that particular circuit diagram, I am showing an asymmetric edge bridge converter, right? So here there is a diode, anti-parallel diode connected to the IGBT. Also in MOSFET you also might have seen that. Can you tell what is the difference between these two? I am talking about power diode and power IGBT. What is the purpose of that anti-parallel diode? For pardon? Yes, if you have an inductor in this case, for example, the trapped energy can be when the switch is off, it can be back to the supply through the diode. Okay, in that way it will also protect the switch also. But the difference is in the MOSFET, if you see the layers like a PN layer, PN layer. So have you heard about the inherent nature of if you cut the semiconductor and if you try to analyze, then you can find that there will be an inherent BJT, inherent diode will be present because of that happens naturally. Okay, because basically what basic is the diode. If you connect a P and N layer, you will get a diode. The rest is everything is like addition. For thyristor it is PN, right? So and then comes all this the way in which you are playing with the carriers, right? Majority carrier, minority carrier, that decides. And then there is voltage control, current control, right? So in the case of MOSFET, that is the inherent diode present. Okay, so that you don't need to. It is actually buzzing, and it can be used very well for trapping that energy, stored energy. But in the case of IGBT, it is not. Okay, so that is why we have to actually while manufacturing itself, they purposefully add this anti-parallel diode. That is the difference between the MOSFET and the IGBT. Okay, but in the circuit symbol you will not find out, because in both the cases you will find an anti-parallel diode. But in the case of MOSFET it is inherent, but in the case of IGBT it has to be purposefully you have to add that one. And you know the inventor of IGBT is Jayant Balika, right? So as that like you have to also appreciate the way in which the semiconductor devices evolved, right? So how they combine the benefit of that BJT and MOSFET to get the IGBT. But even though IGBT is low switching frequency, but still it is rugged, and it can so like more or like you can make an analogy to a thyristor. Okay, thyristor is like how induction motor we call it as a rugged motor. IGBT is also can be placed in thyristor, also can be placed in that way. See, otherwise actually those who worked in the hardware in power electronics, they will appreciate this what I am saying. Because for have anybody used SiC MOSFET, silicon carbide? So the cost of each MOSFET is 2,000 rupees. Okay, and I have to be prepared to afford in case of any failure. See, the SiC MOSFET is known for 1200 volt, 250 ampere, 50 more than that. Okay, I am very well prepared, and I am purchasing that on purpose. But still, we cannot rely on this one, that transient, and the transient will spoil my, so a small transient will spoil my 2000 rupees MOSFET, right? So I have to be very careful in like using these devices. So otherwise I have to spend every time this, right, when I am doing the hardware experiment. So where we left? Yes. So that is what I mean, the commutation, and then as we expected that the proposed having a less number of losses compared to the conventional DTC, and then the switch, the current stress on the power devices. That is also very important, because we are not satisfied with the low frequency. If I am satisfied with the low frequency, I would have used only thyristor and be happy. Okay. The moment I am saying that I am going for high frequency, what does indirectly mean? I am trying to switch on, switch off, switch on, switch off so many times in a cycle. Okay, that will, if I ask you to work continuously for 12 or 24 hours, how you will feel? Okay, you will feel stress. So the same way the device also feels, right? Right. So we have to also take care of that. Anyhow, how somehow we are taking care by applying the thermal paste and then heat sink, by putting fan, and okay, you are doing so much safety, but still, in spite of all these things, so the device will fail. That is not in our hand, and you cannot probe that to see where it gone. So once it's gone, it's gone. So you have to throw the 2000 rupees, right? So that's why these are play, but it is of not much more. Not many people will concentrate on these things, so the stress and that thermal management, heat sink. So usually even my students will do. They will just to see where there is that heat sink is available. They will not worry about the size, the thickness, nothing. They will immediately apply some thermal paste, put the device and screw it, and then put it in the board. That's all they do. But actually we have to properly do the thermal, how much heat it will dissipate. Okay. So otherwise you may end up in losing that device. Okay. So all these stuffs you can do it, how many times it is committing, and then based on that you can calculate the switching losses, right? And then main thing is that switching losses and conduction losses, and thereby I can calculate the total losses, right? So the pie chart shows the losses in the conventional DTC and the proposed for a 250 RPM and for a 750 RPM. So considerable reduction, more than that actually. So this will, at least theoretically, it will improve the efficiency, right, many-fold. Then this is the supply current, not the phase current. Means the current which is drawn from the supply, like VDC is there and IDC. So that current I am talking about, the oscillations in that one. And you can see that we are not drawing any negative current from the supply. And then the source RMS current, basically we call it as. And the number of commutations also is very drastically reduced from 587 to 43 and 309 to 39 and 177 to 32. Okay. So as I said, this is the limitation, that 750 RPM is the limitation. And that way the sector partition increased from 8 to 16, vector is increased from 8 to 16, and in all other aspect, this proposed DTC is performing better than the conventional DTC. And for more details you can refer this, right? The current stress, the voltage stress, the battery life, the capacity requirement and efficiency. And apart from the DTC, that we have also tried the phase reconstruction schemes. That means we try to reduce the number of sensors, because in the first slide we have shown that 4 current sensors are required for 4 phases. So what if at least 1 current sensor is saved? But there is a catch on that also. The moment I say that 1 current sensor I am reducing and I am trying to recreate this, the 4th, for example, let us say D phase, I am not connecting any, and from the 3 measured current I am trying to create this D phase, but I am putting again the burden on the 3 current sensors. That is the catch there. But we are trying to just prove that it is possible. So that is why this one. And these are the asymmetric edge bridge inverter, and you need to measure 4 current, means you need to connect 4 sensors in the 4 phases. And these are the methods which is available in the literature: high frequency pulse injection, split dual bus, improved converter. So people try to also change the converter, modify the converter. Why to go for asymmetric? Instead of that, I will try my own converter. So you can, as I said, you can also design your own converter and you can name after your name, because that is how the Chuk converter, Sepik converter, all those things came into picture, right? So after their inventor, it was named. So similarly, so it is this is not the end of the power electronics. So you can still explore it, and then you can still have a privilege of having your name for that converter, right? So that way you can keep on modifying the converter. Then this is one of the thing which is not our work. It is reported in the literature. You can see that how with only one current sensor, there is no four current sensors here. So based on the single sensor based phase current measurement scheme. And the main problem is in that this non-overlap we want, but actually if the two phase currents overlap, so then it may be an issue. So this is this particular scheme reported in the literature uses only two current sensors, and this particular thing, third literature is completely they modified the converter, and with the help of one current sensor also they modified the converter also. So there is one more available, that is the fourth one, which is multiplex current sensor scheme, where the current sensor is connected for A and C, and here in that way we can save two current sensors. Basically, as I said in the beginning of this particular phase reconstruction, we are trying to reduce the current sensor, and this is the way. So we try to use only three current sensor, and then try to construct the fourth one from this measurement. So rest of the things remains the same, asymmetric, and then this closed loop scheme, whatever I explained with the proposed one for this one. And what we found in our proposed, that we observed that when the conventional, at any point of time here you can see that you take that sector 3 and 4, four currents are drawn at the same time, whereas in our proposed scheme there is only 3, and for some duration it is 0. So we try to utilize this particular feature and try to save one sensor, conducting simultaneously in conventional, but here at most 3 phases, at most, not all the time, 3 phases are connecting in the proposed, and each phase current is 0 for at least 4 sectors. That is also we observed. So then we try to segregate into 4 regions and then identify the sector. And you can see that what is the current sensor. There are 3 current sensor, and what each current sensor measures. And you can always, you can easily come to a conclusion that whatever the missing current can be found from that one, right? So that is how this reconstruction scheme works, and that is mainly because of this proposed DTC and the way in which the current is drawn from the supply. So so that is also given as a simulation result for single phase reconstructed phase current, right? So this is the actual phase current by connecting a current, okay, and then measuring the current in series with that individual phases, and then this is reconstructed phase current. So we can hardly notice any like not much difference is there, and here the sensor currents and then actual phase current reconstructed and error. So the difference in the second one, you can appreciate the way in which it is reconstructed. So what if actually if you put a current sensor and measure, and what if you reconstruct, and what is the error? So the error is very minimal here. So this is the opolarity results taken in a DSO, right? And then under dynamic condition, and this is under steady state condition. So yes, and this is the publication in that one, and this is the setup we have used, and the blue color is the SRM connected to electro brake, dynamic brake. And initially we could not able to actually there are some companies which can give the total setup, because you can see that AHB converter that we have taken from Pragna, and this SRM is from PSG Coimbatore, and then this is from Chalakudi. So what happened is that we could not able to take a whole setup from a single vendor. So we have purchased the SRM, and then we have the thing is that we have to ship it to directly to our institute, and then we have shipped that to the vendor in Chalakudi to connect these two. Then he made a nice arrangement even with that. You can see that a trolley type of thing. We can move that. It is not a fixed one. It's having wheels. So he fitted that SRM and electrodynamometer, right? And a AHP converter, asymmetric edge bridge converter we purchased from Pragna, and then the DC power supply, because we cannot directly, actually even though in that AHP converter, it's having, we can give a 3-phase AC supply, it will rectify and it will give a DC voltage. Okay, that also we can use it, but the problem with that is that what? The controlled current will be uncontrolled during the starting, and that is why we have not used the future of that part. We have used a programmable DC power supply, which because we can achieve a controlled current, we can set the current limitation, right? And that is how. And then later on, the story does not end here. For torque transducer also we purchased separately, and then we have fitted, but that was not I think clearly visible. That is between the coupling between the motor and the dynamometer, right? So and also we try to without torque transducer also we try to measure the torque, and but it was not that much accurate, and that's why we have gone for a torque transducer. And the accuracy of the torque transducer also matters, because according to the rotor position, right? So for every how much angle it will measure the torque, that is also important. That will give you more accurate, right? Suppose for 7.5 or 15 angle, for every 15 angle if it measures, then accuracy will be less. So the lesser the angle, the more the accuracy, right? So also it decides the cost of the torque transducers, right? So we have gone according to our budget, and we have fitted a torque and it is running. And the beauty of that is that we can measure, we can install an app, and then we can also in your mobile you can monitor that. You can see that all those parameters, right? So so these are all some of the things which is already with respect to the rotor position, like how practically you have to based on rotor position, because the first figure it was very perfect because that is the taken from the literature, but this is as per our measurement we have drawn, and then we have tried to produce it here, right? And whatever explained in the simulation and the Opal RT, a part of it we could able to realize it in the actual hardware. And one such thing is the voltage control, which is also a basic control only. So and this is the block diagram for that particular hardware setup, right? And these are the, it is not the Opal RT results, this is the real time hardware results okay, taken. And you can see the voltage applied, the first one the yellow, and then the next one is the current drawn for a single phase, and accordingly the switches for that particular 1H bridge. And then this is for 500 RPM and 2000 RPM no load, and then we have applied torque as well as on no load conditions also. Both the conditions is because if you do the experiment with the no load, then what is the purpose? It is of no use. You have to connect actually a load so that we have to see that whether our motor overcomes that or not, right? So can anybody give some example of that overcoming the load initially, if it is, what is coming in your mind? Any such thing? You can tell lift. See, it is in the ground floor, 5-6 people are standing. Okay, it has to overcome, all are load, you all are load. Okay, your motor has to overcome that, and then so that it will lift the right. So that is very important in any, whether it will overcome the load and it will is it maintain a constant torque or not. So that is an important parameter for any motor. And then this is the hysteresis current control, because if you remember that first one, that is also called as chop control. Okay, because actually we are chopping the input voltage, and then we are trying to keep the current in the limit. Okay, and also we are trying to operate in the positive slope region, dl by d theta region. So that is also implemented, and then the current and the switches, and there are two different that is called soft switching and hard switching. So soft switching is shown here, and these are all some of the, like, whatever the summary of what we had done. So the mathematical modeling, and then the conventional DT algorithm was first developed and then tested, and then we proposed a new one. And first 8 vector 16 sector, and then 16 sector 16 vector, And we also shown in the pie chart it is having low losses. And then phase current reconstruction scheme from the, after studying exhaustive literature, we have proposed a phase reconstruction scheme and closed loop flux estimation approach for a 4-phase SRM based on the 16 sector. And then or verified with the general phase current sampling with a single sensor phase approach to check the correctness. And then we use STM microcontroller for the control purpose, so which is shown here somewhere in the next to the laptop. So we have an STM32 microcontroller, right? So the beauty of that is that sir was also telling about the Raspberry Pi Pico, but there is a limitation, right? The frequency and the number of channel. So actually the caller gone for course, he attended a 1-week course and then he studied. And the beauty is that we can also interface the MATLAB with that one, and then for generating the pulses to that asymmetric H-bridge converter. So he used an STM32 microcontroller from the inductance, phase inductance profile. So that really helped us. The data which is supplied by the IT Delhi, the guy, Dr. Rajesh. So that really helped us to make a mathematical modeling of SRM, and from that onwards we proceeded. So these are some of the works out of that. And this is our actual hardware motor and then the electrodynamic rating. This is the STM32 microcontroller and some of the references. So you are now free to ask any doubt. Thank you. I know that the number of students working in the drives area is keep on going down, and now very few are working. No, we could able to implement that, yes. We didn't face any other. Pardon? No, STM32 microcontroller. This. No, that we have not done. DTC we could not able to verify. That is why I said we have verified only voltage control and hysteresis control in the hardware. The DTC why we could not is that the main culprit is the COVID. 2 years we could not able to assess the lab. He was ready, the student was ready, but it is not. And then his 5 years got. So we have to wind up. But I asked his junior is also working in SRM. I asked him to continue so that we will get at least one good public. We already proven something, but he is very much reluctant. Because the examiner, Professor Shiv Kumar from IT Hyderabad, he was the Indian examiner, and he pointed out that 750 RPM is the drawback. You cannot go above. He was telling that, sir, already sir pointed out it is the drawback, so we will not further proceed. So I cannot do without the help of the research scholar. So he is actually pursuing now in fault tolerant of the SRM. DTC, yes, it is possible. Possible. No, already we have that simulation, and then theoretical background, everything is ready. We have to only execute in the STM and develop accordingly the gating pulses for the asymmetric H-bridge inverter. That's all. Yes. Yes. Yes, that is what we are trying. We are trying to actually keep the motor in that hub, like directly connected to the wheel. But again, in that also BLDC is leading the SRM. Yes. So it is still, as far as my knowledge, not. I don't know any electrical vehicle fitted with SRM. I am doubtful. It is still in the research stage only. But once if people overcome all these whatever that non-linearity is present in this motor, then it is better because of that. So as I said, that rotor is not having any windings or magnet, and because of that it can run it at very high speed, and also it occupies less space. So once we address all these issues, definitely it will also going to dominate in the electric vehicle. The torque ripple, yes. Torque ripple is the main thing when it comes to passenger vehicle. If it is off-road traction, then it is fine. We can implement still. Okay, thank you.
Now, I would like to invite Dr. Rajaram, Chairman IEA Puducherry, to felicitate our resource person with a memento as a token of love. Thank you, sir. Thanks as a word is the simplest form of expressing gratitude. Thank you, sir. It was indeed an enlightening session. On behalf of participants, coordinators, and Department of EEE NIT Puducherry, I thank Dr. Parthiban for an informative talk. Thank you, sir. Thank you all for attending the session. Please note that our next online keynote session by Dr. MP Selvan, Professor, Department of EEE NIT Tiruchirappalli, will commence at 2:30 p.m. All are requested to be on time at SF7 SCB. And external participants are requested to stay back in the auditorium. The next session will be start after the lunch.